Demo Abstract, a real-time control system for replaying motion data, presented by Margot Edwards. Managing your health and fitness using wearable technologies is an exponentially growing market. From a sensing perspective, to enable monitoring for these applications, a motion sensor must be continuously monitor the movements and activities of the user. To enable the research of these IoT devices using modern data-driven techniques such as machine learning, collecting large amounts of motion data is essential to train models. Often this means working with volunteers to perform repetitive experiments over a course of a few hours, days, or months, making this a labor-intensive and time-consuming task. By reusing data from past projects with novel or alternative sensor attachments, new datasets are created, generating activity data for movement recognition without requiring volunteers or time-consuming data collection. We present a real-time control system for replaying data on an electrodynamic shaker, a table that can generate motion based on using previously collected accelerometer traces, allowing for the repurposing of motion data. Our proposed system architecture can be broken down into the following components. To replay acceleration traces via MATLAB's real-time system, traces are played as an audio stream. As human data resonates below 5 Hz, pre-processing removes high-frequency sensor noise. Then, amplification occurs to produce a clear, visible signal with a conversion to a variable current output to the shaker. The shaker is modeled as the amplifier's output current to the resultant system acceleration from a sensor board attached to the recording the generated motion. Acting as a feedback response system, the motion is tuned using a real-time accelerometer feedback applied as filter coefficients to the audio stream. With all sources of data time-synced, the resultant figures represent all stages of the control system, from previous collected input motion to output replayed acceleration. With the particular focus on replaying low-frequency motion, it can be noted that the system does not lose its low-frequency accuracy despite the replaying process. With accurate replaying of human motion successfully replicated from linear single-axis data, future experimentation will occur using multi-axis data where acceleration is not limited to a single axis. Work also includes investigating motion datasets from other sources, such as animals or vehicles. Further, to optimize the performance of the system using data-driven machine learning techniques as a novel implementation on electrodynamic shakers. This project illustrates the potential for the data collection without time-consuming experiments requiring volunteers, as well as generating novel datasets for newly developed motion sensors, such as kinetic energy harvesting sensors. Thanks is given to the project's authors and to support of others acknowledged in this project.